So picking off where we left off, let's go to exercise 2.3-6. And yeah, I've kind of decided that this whiteboard setup is probably the most convenient thing to do. Plus, my voice is relatively close to the camera, which, iPhone camera of the iPhone, the microphone. So you can more easily hear me. And I don't have to move as much, is the funny thing. But back to the assignment. 2.3-6 says, while referring to the searching problem, write pseudocode iterative or recursive. Take your pick according to the exercise. We, of course, are going to choose 1 for binary search. Argue that the worst case running time is theta log n. Okay, so intuitively, we'd repeatedly compare to the midpoint and discard half the remaining range each time. So how would we say that rigorously? Well, and we'd also need pseudocode, mind you. So we're going to choose to do this iteratively, though there's a way you can do this recursively. I think there's like a proof out there. There's like a theorem out there that everything that can be done iteratively can also be done recursively. Don't quote me on that, but I think that's the case. It's like, that's a rough statement of what it would be. But just go ahead and, whoops, forgot to add the binary search. Iterative binary search. Okay, I'm going to check the camera real quick. So, just move this so I can use an arm here. And let's say we have binary search, binary hyphen search. Open parentheses a and x as parameters. So line 1, let's say we have low is equal to 1, high is equal to n, 2, while line 2, while low is less than or equal to high, line 3, mid is equal to floor, open parentheses, low plus high, close parentheses divided by 2, close parentheses. 4, if, line 4, if your a indice, open bracket mid, close bracket is equal to x, we want to return mid. All right, so else if the array indice, the array A, indice open bracket mid close bracket, is less than x, then we want low to equal mid plus 1. Line 6, else I is equal to mid minus 1. 7, return no. So what's going on here, right? Let's kind of get to that. Each iteration halves the interval length so after t iterations, the size is less than or equal to n divided by 2 to the t. The loop stops after t is equal to ceiling function log n iterations. This gives us the worst case time theta of log n. Okay? All right, now let's move on to the next part here. Let me erase this. So you have 2.3-7. What if insertion sort used a binary search which is what we looked at in 2.3-6. What if it used that instead of a linear search to find where to insert? And then, whoops. And it goes on to ask, would, whoops, spelling. English is hard, man. No. But would, computer science don't read good. No, but would the overall worst case running time, improve to theta of n log n. So let's think about this intuitively, right? Start with intuition and then solidify that intuition with rigor. So finding the insertion spot can be big O of log n, but you still have to move elements to make space. And that costs big O of n per pass. So how do we say that more rigorously? Well, at outer iteration j, binary search locates the position in big O of log j time. But shifting the larger elements right costs theta of j in the worst case. Summing theta of j over j is equal to 1 all the way up to n gives theta of n squared. So the asymptotic worst case running time does not improve. Right? Let's move on to 2.38 here in a moment. Let me check that. Okay, on to 2.3-8. So for 2.3-8, that's funny. Describe an algorithm that, given a set S of n integers and another integer x, determines whether S contains two elements that sum to exactly x. Now, your algorithm should take theta of n log n time. In the worst case. In the worst case. Right, so how do we go about this, right? Okay, so intuitively, describe an algorithm that, given a set S of n integers and another integer x, determining whether S contains two elements that sum to exactly. So sort the numbers, right? We sort the numbers, then use two pointers that squeeze toward the middle. Too small, move left, pointer right. Too large, move right, pointer left, right? So let's put this more rigorously. So 1, sort S in theta of n log n time to get a sub 1 is less than ... which is less than a sub n. To set I is equal to 1, j is equal to n, while I is less than j, we have if a sub I plus a sub j is equal to x, return true. If a sub I plus a sub j is less than x, set I, this pointer here, right to left arrow, I plus 1, else, open parentheses, a sub I plus a sub j is greater than x, close parentheses, set j is pointed at front with a right to left arrow, j minus 1. Let's move up here. 3, if the loop finishes, return false. Okay. Now, what's going on here? Well, the two-pointer sweep that performs at most n minus 1 pointer moves. That is to say, big O of n work after sorting. And the total worst case time is n is theta n log n. Simple enough. Some more and less rigorous answers to this, but that's what we have here. Now we get on to the actual heart of the chapter, which are the problems. So let's see here. So for problem 2-1, which discusses insertion sort, insertion sort. That'd be a funny thing, isn't it? Okay. Insertion sort on small arrays and merge sort. So let's see what this is about. Consider the hybrid designed by Ford. No. Consider the hybrid. Split the input into n divided by k sublists of length n. Of length k, sorry. Sort each sublist by insertion hyphen sort. Then merge using the standard merging mechanism. So for the first of it, show that sorting the n divided by k sublists takes theta nk time, theta of nk time. Show that merging them takes theta of n log n divided by k time, and given total theta of nk plus n log of n divided by k, find the largest k is equal to k of n such that the hybrid matches merge sorts theta n log n. Now, how should k be chosen in practice? Right, and so, you know, you can sort of harken this back to one of the first exercises we did in 1.1, where so this sort of goes into the intuition of the thing, but you know, if you saw this exercise that we did in chapter 1, we basically saw, okay, so insertion sort is better than merge sort to a point, right? To a certain point n, and then afterwards it's just merge sort just completely dominates, right? So, and that was, back in that case, I think it was like n is, for n less than or equal to 43, it was like a specific set of parameters by which that was the case. And then we ended up finding that it was 43 based on that, just based on basically plug and chug, right? So, so this sort of thing makes sense if you're trying to like optimize based on how much n, right, like what n is equal to in the thing. So each small array of length k costs what, like theta of k squared with insertion sort, right? There are n divided by k of them. So let's see what this means more rigorously, right? There we go. Okay. Well, I don't know why I pushed it up there anyways. I'm going to have to take this back and erase it. Yeah. So this is an interesting thing here because it's sort of like a little like insertion sort on small arrays in merge sort, sort of like implies that, you know, insertion sort, these arrays, they've already been a thing. They've already been sorted, I guess. But let's take a look at this more closely, right? So with A. So we want to show that sorting the n divided by k sublist take theta nk time. Well, to do this more rigorously, right, so we take n divided by k, we'd simply multiply it by theta of k squared. I say simply, but what does this really get us? It gets us theta of nk. So, right, simple enough, right, though the lengths to which you could go into looking at what each of these things are is, you know, we'll get into that for chapter 3. So B says, show that merging them takes theta n log of n divided by k time. Well, intuitively, merge in rounds, right? So each round scans all n items, and there are log of n divided by k rounds. So a pairwise, I guess, tournament of n/k runs has, you can sort of think about this like in chess terms, I guess. But I mean, like, tournaments are not just a chess thing, they're an everything thing, right? They're an every competition sort of thing. So the pairwise tournament of n divided by k runs has height, ceiling function, log of n divided by k. Whoops, ceiling function, not bracket. Each level's total merge work is theta of n. Hence, theta of n log of n divided by k. Right. So we'll get into more of like what theta actually means, right? So this, I think suffice to say that this works, but it's like, you know, there's a lot of intuition that's sort of like lacking that I could go into, but it wouldn't really mean anything because I'd be discussing like, okay, what is theta, right? It's like, and you could go into a long thing, like a whole lecture of what theta is. Well, not a whole lecture, maybe like a third of a lecture, right? So, but anyway, C says, given total theta of nk plus n, that times nk plus n log of n divided by k, find the largest k, which is equal to k of n, such that the hybrid matches merge sorts theta and log n. So intuitively, we keep the total on the order of n log n. The nk term must not dominate, right? So we need nk to equal big O of n log n, i.e. k is equal to big O of log n. Now taking k to equal theta of log n, that yields nk plus n log of n divided by k, which is equal to theta of n log n plus theta of n times log n minus log of log. Oh goodness, okay, give me a moment. Okay, so which is equal to theta of n log n plus theta of n times, because that's not n of, sorry, that was just n of log n minus log of n, which is equal to theta of n log n. So the largest asymptotically valid choice is k is equal to theta of log n for this case, right? So yes. Now, how should k be chosen in practice? I've got that last part on this problem. Let's see. Well, choose k empirically, you know, like by observation, to exploit catches like a slash branch prediction. So small constraints like k in the closed interval from 16 to 64 are common in modern hardware. And so you benchmark, which is basically, you know, what is that, like, in a way it's kind of like trial and error, but benchmark on target inputs, but it's like it's testing that benchmark. That's what a benchmark is in a way. So that's what a benchmark is. In a way, is what it is, right? So benchmark on target inputs and fix k near the observed crossover. And you'd find the threshold that it should be, and So therein you'd find, you know, a k that's good enough, right? K. Oh no, I just noticed I said that 3 times in a row. That's terrible. But it's also the Filipino flag for, I think it's the Filipino naval flag, but anyway, on to 2-2, correctness of bubble sort. Let me check the camera there. Alright, good enough. And so let's go to 2-2. I have just a few more to go. So, going to be talking about the correctness of bubble sort. Bubble, big bubble, here we go, bubble sort. Open parentheses A, comma, N, close parentheses. So on line 1 we have for I is equal to 1 to N minus 1. On line 2 we have for J is equal to N down, dig deep down to I plus 1. Line 3, if the array A, open bracket, J, close bracket, that specific index of that array is less than this specific index, A, open bracket, J minus 1, close bracket. That's line 3 complete. So line 4, exchange A, open bracket, J, close bracket, with A, open bracket, J minus 1, close bracket. So for part A, we have besides A prime, well, besides A prime being sorted, what else must be shown about correctness? Shown to prove correctness. So this would be like so put in A, and at the very end, this array here. Besides that being sorted, what else must be shown to prove correctness? So, and then part B, give and prove a loop invariant for lines 2 through 4. And then C, using B, state a loop invariant for lines 1 through 4 that proves, it's one thing, the algorithm sorts. We also have a part D, which I almost completely out of room for, but part D, what is the worst case running time? And then we're told to compare this with insertion sort. All right. So for part A, this one, well, we have to say that A prime is a permutation. Fancy variation in a way of the input A. No elements are lost or duplicated. Swaps preserve the multiset. So that's what we want. Now, how about B? Give and prove a loop invariant for lines 2 through 4. So that was for j is equal to n down to I plus 1. And line 3 was if the index j of A is less than or equal to the index j minus 1 of A. So the inner loop invariant with fixed I. So at the start of each iteration, with index j, that is with the condition that I plus 1 is less than or equal to j, which is less than or equal to n, the suffix A, the array A, open brackets j plus 1 all the way up to n, close brackets, contains the open parentheses n minus j, close parentheses, largest elements of the array A, open bracket I, all the way up to n in non-decreasing order. Okay, so it asks us to state a loop invariant for lines 1 through 4, which is what we've done here. Now it's asking, now it also has that for lines that proves the algorithm sorts, right? So we have to prove that the algorithm sorts now. Okay, so this is going to take a lot more board real estate. Okay, initialization. Before the first inner iteration, which is j is equal to n, the suffix is empty. Which, by the way, I like how they use prefix and suffix to talk about these things as though they're like, you know, actual words. I mean, they're formal words, right, in a way. Can't remember the formal definition of a, what is it, you know, a formal language, and then it's, that's theory of computation stuff. But anyway, before the first inner iteration, j is equal to n, the suffix is empty, so trivially true, right? It's like the same way where, I was gonna make another reference that wouldn't make any sense to you, but well, it depends. I mean, if you're there and you know the reference, it's like how a subgroup has to be non-empty. Spit all over the board. Gosh freaking dang it. That's stupid. No, but let's see here. Maintenance, comparing comparing the array A open bracket j minus 1 and A open bracket j close bracket, oh whoopsies, A open bracket j minus 1 close bracket and A open bracket j close bracket, and swapping if out of order ensures that after the iteration the larger of the two resides in the array A open bracket j close bracket, that indice j, keeping the largest elements packed at the right in order. So what would this do? Well, decrementing j preserves the claim, right? Would it, let's see, let's think about this a bit further. Comparing ensures resides in keeping the largest elements packed at the right in order. Decrementing j preserves the claim. Yeah. Okay, but how about termination? When j is equal to I plus 1, the suffix, prefix, suffix, first part and then end part, the suffix A of I plus 2 all the way to n holds, that holds the open parentheses n minus I minus 1 largest elements of the array A from I to n. Thus, the array A at indice I plus 1, so A open bracket I plus 1 close bracket, is at least, oh, not supposed to do that. It's like one word, right? Nope, 2 words. I could have done that. Oh well. At least as large as any element to its right and the minimum of A of the array A open bracket I all the way to n close bracket, thus A at I plus 1, so A open bracket I plus 1 close bracket is at least whoa. Minimum of this, right? A plus 1 is at least as large as any element to its right. Oh my goodness. I just repeated a line, didn't I? Shows how tired I am, I guess. I don't know. Let's see. I was gonna say, I thought I caught it there for a moment, but then I was like, no, it's fine. Let's see. Thus, this is the case here, is at least as large as any element to its right, and the minimum, yep, I repeated, sorry about that. Sometimes you gotta be careful, and the minimum of A from I to N must be at A, the array A, open bracket I, close bracket, after one more comparison / swap step. Equivalently, by the usual bubble variant, after completing lines 2 through 4, A open parentheses A open bracket close bracket A open bracket I close bracket is the ith smallest element. So by the way, the reason I keep saying this is like I keep saying like the bracket thing. It's like one thing. It's like, well, it's easier to kind of like read along as though, like if this is playing in the background, for instance, that you can just kind of hear the thing and maybe it'll register. There's better ways of saying this, right? But it's like that. It's also, I'm going to be looking at different cycles and stuff. There's like this notational thing I'm going to be looking at, which is why I keep saying that. But where was I? So equivalently by the usual bubble variant, after completing lines 2 through 4, A open bracket I close bracket is the ith smallest element. So that works for termination, and therein we end part B. Because we have shown we have stated a loop invariant for lines 1 through 4, and we've proven that the element that the algorithm sorts. Sorry. Now let's go on to part C. It says using B, state a loop invariant for lines 1 through 4 that proves the algorithm. Wait. Sorry, I think I've been saying part C for part B this entire time, but part B was given prove a loop invariant for lines 2 through 4, which is what we did. Now, part C says using the state loop invariant for lines 1 through 4 that proves the algorithm sorts. Right. So, goodness gracious. So, C is about this, well, outer loop invariant. And, well, at the start, of iteration I of lines 1 through 4, the prefix A from 1 all the way to I minus 1, A open bracket I all the way to, 1 all the way to I minus 1 close bracket. Now, this prefix contains the I minus 1 smallest elements in non-decreasing order. Elements themselves, not the iteration thing. I mean the iterated, something like that. Iteration I. Yeah, so in non-decreasing order. So by B, the inner pass, the inner sort of, goes past it. The inner pass places the next smallest at the indice I of the array A, so A open bracket I close bracket, preserving the invariant. When I is equal to n, the whole array is sorted. So we have that, right? Way we can have our cake and eat it too. So that's that. Now let's move on to part D. It's about time. Yeah. So for part D, which was what is the worst case running time, compare that to insertion sort. So the time the inner loop performs summation I is equal to 1 to n minus 1 of n minus I, which is equal to theta n squared comparisons. So in the worst case, a constant fraction of these cause swaps. So time is theta of n squared. Now insertion sort we go. Insertion sort also has theta of n squared worst case time. Though, however, it typically performs fewer moves in that same sort of time frame. So performs fewer moves and is faster in practice. What is it like? Trying to think what this could be compared to. So completes the thing in fewer step sizes. I don't know if that's accurate though. So, but suffice to say, it typically performs fewer moves and is faster in practice. So that's all I'll say about that for now. Now let's move on to 2-3, correctness of Horner's rule. So this is an interesting one. So 2-3, as I mentioned, as I said, correctness of Horner's rule. Gosh dang it, Horner. Freaking Horner. No, but what did he do? There's a lot that he's done. None of which is like particularly evil or anything. It's just he's Horner, so you've gotta humble him a bit. But anyway, big P of x is equal to the sum from I equals 0 to n with a sub I times x to the I using Horner. Well, sorry, that's not Horner. Well, we gotta evaluate this using Horner. Yeah, the actual Horner algorithm. Gosh dang it, Horner. That's open parentheses a, comma n, comma x. So that's p is equal to 0, 2 for I is equal to n down to 0, 3, p is equal to the array a open bracket I close bracket plus x asterisk b p, so times p, sorry, 4 return, that's line 4, whoopsies, return p. So what does it mean more particularly whenever it says evaluate? So it wants you to, for one, give the running time. Give it the running time. If you don't, your family's at risk. No, but give the running time. This has got to be the most unhinged lecture series on algorithm analysis in existence. Never mind the accuracy. Oh my gosh. Write naive pseudocode. And compare run times. And see, prove, gosh freaking dang it, Horner. Prove Horner's correctness via a loop invariant. Freaking Horner, man. Okay, so how do we go about doing this, right? Goodness gracious. Okay, let me check the camera real quick. Always gotta check the camera because I'm always kind of afraid that it'll just sort of randomly shut off and then it's like I'll be talking to nothing. I mean, I'm technically talking to the camera, which is technically, you know, nobody's really listening. It's only a hypothetical person that's listening, right? So, but anyway, let's see about this. Yeah, the camera is Wilson. You are Wilson if you are listening on the other side of this. But anyway, for A, time the loop executes order 66. No, it executes n plus 1 iterations. So what is that? Each does big O of 1 work. So theta of n, right? So theta of n. Now let's look at the B, which is to write naive pseudocode for this. Write naive pseudocode and compare runtimes. So, gosh dang it, why did I write that down? Freaking heck. Okay, so naive evaluation, right? So naive polynomial, poly is very naive. So naive hyphen poly, open parentheses a, comma n, comma x. So for 1, p is equal to 0, 2, for I is equal to 0 to n, 3, pow is equal to 1, which is pretty cool. 4, t is equal to 1 to I, 5, line 5, pow is equal to pow times x, 6, p is equal to p plus array a, the indice I, so a open bracket I, close bracket times pow, and then line 7, return p. So let's see here, part B. So for part P we've got to have that naive pseudocode, which we now have. This is I'm a bit better, but not I'm a bit worse. No, so terrible. No, but the inner power loop. Well, oops, that looks like a W. Can't have that. I mean, but the cursive L looks like a gamma anyway, right? I mean, oh well. The inner power loop costs theta I. So summing gives the summation from I equals 0 to n of theta I, which is equal to theta n squared. Goodness. Okay. So Horner's rule. So Horner's not Horner's rule. Freaking Horner. So Horner's theta of n is asymptotically faster. Though it's not always better, right? So okay. Yeah, so we compared the runtimes there. Now let's move on to part C. I don't know if I even mentioned the time at the start of this, but that's fine. CS is to prove Horner's correctness via loop invariant. Freaking Horner. It's always just ruining things. Okay, no, not really. I don't know why. It's just a running gag. Has no meaning. Not really. Let me get a different marker. So what is C asking? Prove Horner's correctness via loop invariant. Right. So at the start of each iteration, with the index I, under the constraints that n is greater than or equal to I, which is greater than or equal to -1, P is equal to the sum from k equals 0 to n minus I minus 1. And that is the summation of a sub I plus 1 plus k. And that is, this is one thing right here. That's multiplied by x to the k. Which is, that's a wild sub thing right there. But that's for indexing, right? So, you know it's important. Maybe you don't know it's important. But this is at the start of each iteration. So consider it important enough for now, right? So initialization. So this is I is equal to n. The sum is empty, so it is declared. But actually, so P is equal to 0 matches line 1. Right? So that's pretty good. Usually initialization, that's usually what happens for these. But maintenance. Usually people just say maintenance, but it's maintenance. Oh well. Maintenance. Update. P. Okay, pointer. So that's a point. So that's a right to left arrow from A plus XP to P. P takes that, so transforms. That transforms. P is equal to A sub I plus X. The summation times the summation k is equal to 0 to n minus I minus 1 of A sub I plus 1 plus k, all of that times x to the k, which is equal to the summation from k is equal to 0 to n minus I of A sub I plus k times x to the k. Didn't mention the parentheses there, but I think, okay, so if you didn't, so it's like open parentheses A sub I plus k, close parentheses, times x to the k, which is the invariant with I, that's a right to left arrow from I minus 1. Pointed to. I don't like being pointed at. I don't know, depends what for. Okay, so now we have the final part, which is termination. So let's look at termination in this case. So for termination, whoops, is equal to -1. That's a 1. We obtain P is equal to the summation from n, from k is equal to 0 to n, A sub 0 plus k, that's multiplied by x to the k, which is equal to P of x, which is what we wanted. QED. Okay. What is it? Quo in medias demonstratum, something like that. Okay, so we've done all parts A, B, C. for for problem 2-3, we've shown the correctness of Horner's rule. Freaking Horner couldn't do it himself, no. But we gave the running time, we wrote native pseudocode, compared the runtimes. Okay, so let's go after this last problem here of chapter 2, which is about inversions. Then we'll call it a day. Well, we'll call it the end of this video. We'll pick up with something else here in a bit. Check the camera. Camera's good. Oh boy, that's me sitting down. That's the sound right there. Okay, but anyway, 2-4. 2-4 inversions. Inversions. So let the array A open bracket 1 colon n close bracket contain n distinct numbers. They are not stink, they are distinct. Okay. Goodness. If I is less than j and a open bracket I said I, there we go. I mean, if you do it in the other direction, that makes it an I. Close bracket is greater than or equal to a open bracket j close bracket, then the coordinate, no, then, well, kind of, then open parentheses I comma j is an inversion. So for this problem, we have part A, just tells us to list the 5 inversions of 2, 3, 8, 6, 1. It's this whole little insertion looking thing. And then B, we're asked to, which array on the set from 1 all the way up to n, a 1 comma all the way up to comma n, has the most inversions. How many is that? That's also in part B. So that's something. Let's ask 2 questions for 1 part. That's fair, right? No, but relate insertion sort. Insertion sorts running time to the number of inversions. In part D, give a theta n log n algorithm to count inversions. So that is all of what is given to us from exercise 2.4. Okay? 2-4. Guess it's like, well, how would I say this? So, what is it like? It's like, I don't know. Is it like pre-image versus image? I'm not entirely sure about that. But it's It's kind of like we're going back in time to a thing, right? But I don't know how accurate that actually is. I'll just stop talking and try to, well, I won't stop talking. Probably not until either I'm asleep or dead, right? But the inversions in this particular case, you know, they are as follows. So, well, actually, no, because it gives you a specific definition of what an inversion is. So you just, you know, plug and chug in relation to what the definition of an inversion is with relation to the array, and you should be able to get your inversion, each inversion, quite well, right? So 2, 3, 8, 6, 1, right? So think about that. Okay. So it's like, well, how many distinct numbers are there in this? Well, there's 5. Okay. And what would that look like if we ordered them correctly? Well, look like 1, 2, 3, 6, 8. 6, 8. Can we have 6 and 8 though? Let's think about that. For the inversions, I mean to say, can we actually have 6 and 8? No. So, but we have the sort of, what is it? How do I say this? If I is less than j and its place in the array is greater than place of j, then that coordinate pair of I and j is an inversion. So what can we really make out of? So let's say we plug in 2, right? Well, this is an array. Plug in the first section. It's always going to kind of be 5 except for one of them. So let's think about this. So for inversions, what do we get? Well, we get the ordered pair 1, 5, 2, 5, 3, 4. Sorry, open parentheses 1, 5, comma. So these are the inversions that we get. Open parentheses 1, 5, close parentheses. Open parentheses 2, 5, close parentheses. Next inversion we get open parentheses 3, 4, close parentheses. Next inversion, open parentheses 3, 5, close parentheses. And the final inversion, which is open parentheses 4, 5. Right? So again, you can go back to the definition and see like, okay, how exactly will this fit? Fits, it works, right? So I don't know how else to, I guess I could go like by step, right? So something I could do. Okay. I'm not really sure how I'd show that. It's kind of, what is it? Not self-explanatory, but it's a definitional sort of thing. Don't really have a full-fledged sort of thing written up yet, but perhaps we'll get to another one where I can show that more explicitly. But for now, suffice to say, these are the inversions. Well, let's put it this way. So the first one, is that less than some I is less than j. I is less than j, right? So is I in this case less than j? I is less than j. And it's like, well, what about the index? What about what's actually at the fifth one? So is it the case that at 2, so this would be 2, right? Is it the case that 2 is greater than 1? Yeah, oh, it looks like a 2. So yeah, okay. So let's do it this way. So at the second indice, at the fifth indice, right? So at the third, third, the fourth, third, the fifth, right? So the definition had I is less than j, and the indice, the actual value of that, right? So in the array is actually greater than, which means ij is an inversion. So let's go ahead and, just sort of backwards check this, right? So is it the case that 1 is less than 5? Yes. Is it the case that 2 is greater than 1? Yes. Okay, put it in. So how about this one? Well, is it the case that the first indice is less than that 2 is less than 5? Yes. Now, is it the case that 3 is bigger than 1? Also yes. Now, going on to the next one. Is it the case that 3 is less than 4? Also yes. Is it the case that 8 is bigger than 6? Also yes. Okay, so let's move on to the next one. Is 3 less than 5? It's like, yes. Okay, is 8 bigger than 1? Yes. So, and you continue on like this, right? So, and then we finally get 4, 5, which is just, well, that's 6, this is 1, right? So it's like 4 is less than 5, of course. 6 is greater than 1, of course. So that's pretty much like a detail how to really get those. How to, it's more of just, this was a reverse sort of engineered thing, right? So, but B asks a switch array on the set from 1 all the way to n has the most inversions, and if so, how many? Well, the reverse sorted array from n to n minus 1 to all the way to 1 maximizes inversions. Each pair, ij, with I being less than j, is inverted. And that gives us this combination n2, which is equal to n times n minus 1 over 2. So it's the reverse sorted array. That's what we want. That maximizes the number of inversions. Okay. And that sort of makes intuitive sense, right? So it's like, well, if you do all of this sort of stuff and it's just kind of chunks to these results, well, first, I thought that was a fire alarm. Let's relate insertion sort Whoops, almost wrote the entire thing again. So C asks us to relate insertion sort's running time to the number of inversions. Well, in insertion sort, each swap of adjacent out of order elements reduces the inversion count by 1. Hence, the number of element moves and therefore and thus time beyond scanning well that's theta of the number of inversions, right? So the total running time then is theta of n plus number of inversions, which is theta n squared in the worst case. So that's how they relate. They have the same worst case time, running time. Now let's see about getting that algorithm to count inversions with that specific running time of n log n, shall we? Camera's still good. Let's see, is it? Yeah, it's still good. Okay. So, let's see about this, right? Move this away so I can have some elbow room. But, so D said give a theta of n log n algorithm to count inversions, right? So well, what do we know? That's n log n in terms of running time. Well, merge sort is, right? So modify merge sort while merging two sorted halves, L left and R right, whenever an element from R, I don't always have to cursive the L, but you know what, it's fine. From R is copied before an element from L it contributes to the order of, well, the number of L remaining inversions. So summing these counts over big O of log n merge levels So summing these counts over big O log n merge levels. So summing these counts over big O log n merge levels yields total time theta of n log n and the exact number of inversions. Gosh dang it. There we go. All right. So that's pretty much for all of the exercises and problems in Chapter 2. And that is it for now.